Everyone, today we're looking at combo circuits where we're going to put series and parallel capacitors together in the same circuit and show how you solve for the charge, the voltage, and the energy that are in each of the capacitors. So let's look at an example. Alright, so here's our setup. We've got 5 capacitors hooked up to a 10-volt battery. What we need to do is solve for the equivalent capacitance, the charge on each capacitor, and the voltage that's on each of the capacitors. When we see a combination circuit like this, there is series and parallel going on everywhere. What we want to do is bring this into one simple circuit. So the first thing that I would do is take these two sets of capacitors and they're side by side to each other, which means that they must be in series. There's only one path to go. Once the charge leaves the battery and hits that junction, it has to go across both capacitors. So if that's the case, they must be in series. And to do capacitors in series, that's our equation of 1 over C1 plus 1 over C2. So I'm going to do that actually for both at the same time to show you how we can simplify this circuit. So I've set up the series equation for both of those series branches, a 1 over 2 plus a 1 over 3, and a 1 over 5 plus a 1 over 1. Remember what common denominators here? For the top branch, it's 1/5 plus 5/5, or 6/5 equals 1 over C. Remember, take the inverse of both sides to get the overall capacitance. And down below, it's 3/6 plus 2/6, which is 5/6. Again, take the inverse so that we don't have the wrong equivalent capacitance. Essentially done is we've taken those two sets of capacitors in series to a 1.2 microfarad capacitor and a 0.833 microfarad capacitor. Now we've got two capacitors in parallel. So what we want to do with two capacitors in parallel is add those up and combine them into one capacitor. That's easy because parallel gives us C1 plus C2, or you just add up all the capacitors that are in parallel. Shrinks us into an equivalent capacitance of 2.03 microfarads. Now we're left with two more capacitors. These two capacitors are in series, so we're going to do the same thing we did again. This final equation here is going to give us our total equivalent capacitance for the entire circuit. So in the end, the overall capacitance is 1.34 microfarads. I took a 10-volt battery, connected them to those 5 capacitors, and by doing all our rules for finding capacitance in series and parallel, I was able to figure out that I could replace all 5 of those with a 1.34 microfarad capacitor. Now that I know that, I know the capacitance is the ratio of charge per volt, I know the voltage, I know the capacitance, so I can tell you the charge that's going to come out of this battery. It's going to be 13.48 microcoulombs of charge. So now we have to kind of step back and see how that 13.48 microcoulombs is going to move through our entire circuit. If I take one step back, I've got my two capacitors that were in series right before we combined them, and I know that the charge is 13.48 microcoulombs. Now they're in series, so if we follow the rules for series, each of these capacitors has the same charge. So the charge on the first capacitor here is 13.48 microcoulombs, and the charge on this capacitor is also 13.48 microcoulombs. Now remember that this 2.03 here is not really a 2.03 farad capacitor. It is a hidden series and parallel combo that we looked at before. But the 4 microfarad was the original one we had from the beginning of our problem. So since I know the charge and I know the capacitance, I can solve for the voltage here and tell you 3.73 volts of energy are across that first capacitor. And since these are two capacitors in series, they're going to share that voltage. That means that the remaining voltage out of the 10 from the battery, the 6.63 volts, must be across this, again, this hidden 2.03 microfarad capacitor. So let's take one more step back and use this info we have here about the 6.63 volts and see if we can spread that out among our other capacity. Remember that 2.03 was really these two capacitors in parallel, and since we know that there's 6.63 volts on these two in parallel, the rules for parallel says that both of these have 6.63 volts. So that's another step in the right direction. But we have to go one step further there and figure out how much charge is on each of those branches. I know the capacitance and I know the voltage now. On the top branch, the charge is 5.3 microcoulombs, and on the bottom branch, we have 7.96 microcoulombs. Adding those two together gives you around 13.48 microcoulombs. So we are at the amount of charge that we said that parallel branch needed to have. It had to have the same as that 4 microfarad capacitor from our first breakdown. Now we know the charge on each of those. But remember, these two capacitors are not really a 1.2 or a 0.83. We have to take them one step further back. So here we are at the end. At the very beginning, we had this setup with one capacitor attached to a branch that had two capacitors on each of the branches that were in series with each other. Since those two branches are in series, I know that each of these capacitors here has, on the top branch, a charge of 5.53 microcoulombs, and I know that each of these capacitors down here has a charge of 7.96 microcoulombs. Because they're in series, so they've got to have the same charge on each. What they're going to share now is that 6.63 volts that we said they each of them had before. Solve for the voltage. On the bottom there you can see 398 volts and 2.65 volts. Add those two together and you'll get the 6.63 volts that those two must share. And on the top, we're going to do the same thing. So you can see that 1 microfarad capacitor has 5.53 volts, and the 5 microfarad capacitor has 1.1 volts. Adding those together should also give you around the 6.63 volts that we said that those two parallel branches had. So that's what you do when you see a combination circuit. You've got to shrink down your circuit into one equivalent capacitance to figure out the amount of charge that goes through, and then you go backwards and reconstruct your circuit, making sure you follow the rules for series and parallel. But we could also have the setup here where we take two charged capacitors and hook those two capacitors together. And what happens when we charge the two capacitors independently and then reconnect charged capacitors? So the way I'm going to show you this is I'm actually going to put out capacitors and show you what happens when we charge them up and connect them to each other. So in this setup, I can throw in two capacitors, and I need a source of potential, so I'm going to have the battery. So I got two capacitors. One's a 0.1 farad capacitor, and one's a 0.2 farad capacitor. I've got a 9-volt battery here that I'm going to hook up to each of these capacitors and charge them independently. So the first one I'm going to hook up to the battery. We said the charging process will end when the capacitor reaches the voltage of the actual battery. So if I pull out a voltmeter right now, I should see 9 volts across. Now, if I take the second capacitor here and charge it to 9 volts, if I try to connect the two capacitors together, nothing will happen. Even though there's more charge on one capacitor than the other, they're both at the same potential. The only time we get charges to flow is when there is a potential difference. So let's just hook this up right now. We've got two capacitors, one at 0 volts and the other one at 9 volts. The question could be, what final voltage do these two come to? So here's how we're going to hook this up. We're going to connect these two together with wires. One of these is charged at 9 volts and the other one is at 0 volts. So like we talked about with equipotentials, these two capacitors will flow and move charges until they reach the same voltage. So what I need to do is see what the total capacitance of our setup here. Well, when this finally charges, this side of the capacitor is going to be positive and this side of the capacitor is going to be negative, which means that we technically have a parallel setup when we connect these two capacitors together. So the overall capacitance is easy. We can do C1 plus C2. And we know that C1 is a 0.1 farad capacitor and C2 is a 0.2 farad capacitor. So the overall capacitance is 0.3 farads. Now, knowing capacitor 1 has 9 volts and its individual capacitance was 0.1 farads. So I could tell you the charge on that first capacitor is 0.9 coulombs. Since I'm not connected to a battery, What that means is that I can't gain or lose any more charge. The battery's not going to pump more charge onto the plates. So all that's going to happen is these plates are going to redistribute the amount of charge, this 0.9 coulombs. And they're going to do that until they reach the same voltage. So let's see what that common voltage is going to be. I know my total capacitance is 0.3 farads, and I know the total charge available is 0.9 coulombs. So using C equals Q over V, solve for the common voltage that these two equivalent capacitors have to come up with. And if you do that, you should get 3 volts. So when all said and done here, if I take 2 wires, and it will happen quickly, so if I take the 2 wires and connect them, the charges have redistributed now. You can see that the larger capacitor up here has more charge and the smaller capacitor has less charge. So the bigger capacitor has more room. But if I take the voltmeter and I put it on either side of the capacitors, I should read 3 volts. They did discharge until both capacitors here, you can see I'm checking the bottom one now, are at the same potential. So when you hook 2 capacitors together, think of them like capacitors in parallel. Look for the overall capacitance and know the charge can't gain, it's just going to redistribute itself. So that's how we go at solving for connected capacitors and capacitors when they're in series and parallel at the same time, those combination circuits. So practice some problems, and we'll see you next time.